Okay, well, thanks again for this opportunity. It's kind of nice. I've been involved with TFAWS for a long time. In fact, I remember several years ago, I went to one that was held at NASA Langley, which was kind of fun. Um, so today, I want to talk about modeling in cabin environments in general, and more specifically, how to model coughs accurately. This work is actually collaborative, so I've listed some of the co-authors here, but that includes Miller von Perich, who will talk about some of his work, Prashant Shankaran, Scott Lewinsky, Aaron Bird, Matthew Stasia, and Olivia Brokla, all of which are pretty much scattered globally. And they've entrusted me with talking about this issue. So thank you again, and I'll go ahead and get started. I'm going to walk through maybe two different examples. The first, I want to talk about the role of simulation in ECS design. And specifically, what I want to talk about is leveraging a mixed fidelity approach to look at overall ECS system performance, how that fits into modeling the cabin environment and safety within the cabin environment. Then I'll talk about aerosols, the anatomy of a human cough. We'll talk about statistical versus discrete methods, and then we'll see kind of the impact of that on ECS design. There were two results I was hoping to show today, which is unfortunate that I was unable to get them through the cluster. We ran into an IT issue twice, and so the results I show will be preliminary. We do have a webinar that will be likely in mid-September with one of our partners who will talk about those results in a little more detail, but we can get into that here in a second. Okay, so a couple of things about ECS that most people don't really think about. ECS does have a significant impact on the overall energy efficiency of most single aisle and dual aisle aircraft. And there has been a notional desire to try to get to carbon neutral. And to do that, of course, means that we have to look for ways to increase efficiencies. Now, most people start to think about efficiencies and go directly to either lift drag, maybe moving away from tube wing, or perhaps looking at different engine technologies, whether hybrid electric propulsion. But there's another bit that you have to consider, which is the ECS system. Air traffic has been growing, and of course, we're in a bit of a lull right now, and I'll talk to that here in a second. But generally, we still are seeing and anticipate seeing an annual growth rate in air traffic in the 3 to 5% range. Our current technologies won't necessarily get us to this carbon neutral goal. And that's one of the ways we feel simulation can play a role here, is to look at strategies to mitigate some of the energy utilization for ECS, which, as I mentioned, is about 30% of total energy production use for an aircraft. So safety has become really critical for the industry. Specifically, we want to get to a point where people are comfortable flying, and a lot of that comfort has to do with understanding the relative risks of flying in an enclosed environment. And you can see this is actually from my hometown, SeaTac Airport. From the February timeframe to today, we've seen a pretty significant dip in air traffic down to about 16,000 passengers a day. We were averaging close to 50,000 before the current situation. And so how do we impact that? Well, we do that by helping raise awareness about the relative safety of flight and to understand what mitigation strategies are available to airframers and integrators to increase safety. And the last bit, of course, is in addition to the safety aspect, there's a desire to improve relative comfort. And that comfort and safety is often gauged in relative temperature and temperature variation, velocities, as well as pressurization and humidity, both of which tend to have a pretty big impact. If you're lucky enough to fly on a 787, you'll know that the pressure, relative pressure in the cabin is about 15% higher, and you have significantly more humidity. So that tends to make air travel a lot more comfortable. So when we think about cabin design, one of the groups that we've been working with for some time is looking at how an ECS system can provide both adequate cooling and a comfortable environment? And how can we leverage simulation to maximize energy efficiencies? The main objective here is to design a robust system that can be used as part of certification requirements. So in this case, we want to leverage simulation as one component of means of compliance for single-aisle aircraft certification. So this is MOC2, which is certification by analysis, and it is one component of an overall work instruction that can be used with the FAA or the like. So in this context, then I'll talk briefly about early design sizing, how we can leverage low order methods to evaluate system performance before we have geometry. In effect, we can take some basic design criteria and develop a model, a system model of the overall aircraft, leverage that with some late cabin design improvements. In essence, we can then look at the 3D effects once we are in the planning phase. And then we want to talk about how you can leverage a mixed fidelity approach where you couple your system model to a high fidelity CFD model, and then use that as a mode to model ECS path failure with the idea that you can use results from that as part of your means of compliance. So let's kind of go through that example, and then we'll talk about particle distribution and COF modeling as a result. So oftentimes when we work with integrators, probably the biggest thing that starts any aircraft program is, okay, well, how big is it? Is it going to be single aisle? What kind of propulsion system? Is this going to be electric, hybrid, turbofan? What are the weight objectives, the range objectives? What kind of air, let's say the icing protection system will be used? And these can be used to start to put together some requirements. And those system requirements then will be relative BTUs required, the robustness of the system, redundancy, desired weight, and then, of course, the part that relates to this conversation, airflow and filtration. And that can be used then to develop an initial system design. Now, mind you, this system design is based on typically available components, and it's kind of the start point for this type of analysis. So as you're probably aware, the ECS system is pretty complex. It not only provides air conditioning. For those of you who aren't involved in ECS design, one of the biggest challenges you have is you may have 200 or 300 passengers all generating a tremendous amount of heat. So the big problem you have within the cabin environment is keeping it cool. So you need to have adequate cooling to keep the temperature comfortable. At the same time, you need to be able to look at the pressurization system, the impact of ice protection if you use a bleed air system specifically, whether you're using cross-engine starting strategy. And it's really, how do you bring those things together? So on the right, what you see is a rudimentary model that talks to where the ECS packs through the circulation system and into the cabin environment. And we can actually use our system model then to evaluate the airflow requirements, cooling requirements, and we can look at different scenarios just starting with that 1D model. Then that 1D model can feed into the types of analysis we typically get into and on the 3D level. So specifically, when we want to look at mixing or circulation, we want to use typically CFD, cabin modeling and cabin comfort, ducting, avionics cooling, and of course, looking at ice protection systems. So once we get into these, let's say 3D fidelity models, we want to look at CFD as a way to evaluate cabin ventilation, thermal comfort, which is a measure of relative comfort of a passenger. It's based on some literature data. The basic idea is that you can understand, based on velocity profiles and temperature gradients on each passenger, you can understand their relative comfort, and it's typically done in a percentage. So it can be a low percentage is uncomfortable, high percentage is comfortable. Air delivery systems typically are not done using high fidelity modeling just because there's not, it doesn't really lend itself to that kind of analysis. Bleed air systems certainly fall into the category of high fidelity, as well as ventilation and ducting. So let's talk about how this can all be put together into a mixed fidelity case. So the case that was chosen was actually looking at an ECS pack failure at 100 seconds into cruise. So what you're looking at, again, on the right is the system model, and we have our two ECS packs that are going through the pressurization system, and they actually go into different zones in the cabin. We chose one zone to look at just because of convenience. And the basic idea is that we are going to turn off one of our ECS packs and then evaluate the CFD environment inside the cabin. So what you see here is actually looking at the relative comfort over time for the different passengers. We call them Jake and Jillian. It's not really critical in this particular case. And as the animation, I'll kind of go through this quickly. So this was done using Star CCM Plus. The model itself was run over 1,300 seconds. What we measured basically was the cabin environment in terms of velocities and temperature profile. And we fed the temperature, humidity, and pressure information back to our system model. And the system model then responded and provided additional cooling. So what you see in the animation is, as it kind of recycles one more time here, is that you see the steady state environment. You can see the heat plumes coming off the passengers. At 100 seconds, we have the ECS pack failure. You see the temperature inside the cabin actually goes up rather quickly. Then the system responds of providing additional cooling capacity, and that's actually used to get to a steady state. This information then can be fed back into the overall requirements documentation to see, well, could we keep the temperature under 30 degrees, which I believe is the certification requirement. Okay, so let's talk about that in the context of contamination with CFD. And so we've been doing this type of work for a long time in different capacities. Some of the work we've done early on related to clean room design, specifically looking at different species moving within the clean room environment, how much airflow is required from the HVAC system, and evaluating whether or not we can purge those gases and make sure that contamination is kept to a minimum. The other part of this analysis is really things like operating rooms, where cross-contamination, again, is a big issue. And so we actually looked at modeling operating rooms, again, to look at the overall flow and to ensure that contamination was minimal in this environment. So how do we do that? Let's talk a little bit about the CFD that we did. So in this particular case, we actually modeled a cabin environment that included 5 rows of passengers. A couple things about those passengers. You'll notice if you look closely that they are all different sizes and shapes. The main idea here is that we have a tool that allows you to generate human models that you can use in environments. And we wanted to make sure we had a heterogeneous environment of people to get the best possible result. This was done using a hexahedral mesh. The 2 meshes that we looked at a fine model. Again, remember, these are both unsteady. So the fine model was about 28 million cells, and the coarse model we ran was about 10 million cells. In both cases, we saw more or less the same basic behavior. The variance between the 2 models was quite small, and therefore, for most of the work I'll show here today, we focused on our coarse model. Let's take a quick look. So what you're seeing now is the local velocities inside the cabin. So these were URANS simulations. We ran them from 2 to 4 minutes at a humidity of about 10% in the cabin, which is common for this type of analysis. The human models, as I mentioned, were part of a package we call Siemens Jack. The temperature of the bodies were set based on literature information. And we used the thermal comfort model and looked at everything from respiration, from the nose, gaspers on and off. For those of you who maybe aren't aware, gasper valves are the valves above your seat that you can use to provide local air conditioning environment. So this was kind of where we started on the cabin flow, because you need to have your cabin flow pretty well understood if you want to understand propagation of contaminants in the cabin flow. So I want to talk about the physics of the human cough. As you might imagine, it's quite complex. And although there are some people who've done a fair amount of literature reviews of the human cough, it's still not perfectly understood. There's high variability between people. There's also variability in terms of how people cough. Some people cough into their arm, others into their hands. Others cough up. Some people cough to the side. Some people kind of close their mouth a bit. So you kind of have to think about more of a statistical distribution of coughs. We're not going to do that in this paper just because of the computational resource limitation. But given that high variability, though, there are some standard curves in terms of relative time of a cough and velocity. So we've been fortunate enough to work with some medevac simulations, specifically looking at contamination due to transporting sick patients. So the main objective of this study was to evaluate the relative concentration of drops that impinge on surfaces and recirculate inside the cabin environment. And this was done well in advance of the current pandemic. So this was not in response to any work related to COVID-19. This was actually done just by the Department of Defense to understand what they need to take into account. So the models that were used in this case, we looked at about 100,000 Lagrangian particles, and the main objective here was to model those throughout the flight and to understand how many of those particles are actually recirculating and understand the airborne particle count. So the output helped in terms of the design of the cabin to mitigate cross-contamination. This was done using some design optimization strategies. I believe HEEDS was involved in this work. And again, the main objective was to figure out the appropriate orientation and ventilation strategies to mitigate cross-contamination. All right, so how does that model into cough? We get into some of the physics here. So a couple things to point out here is that when we think of cough, one of the things we know is that if you had someone standing in an environment without circulation and looked at the propagation of cough droplets, you would see that larger particles, larger droplets, and those are, in the 700 micron range, they tend to fall directly to the floor and they stick. So you don't have to worry about them entering the environment. Medium droplets tend to go a little farther, but again, due to the effects of gravity, they tend to basically fall to the ground. Those smaller droplets and aerosols, however, can linger in the environment. Now, based on a number of parameters, one can model what that distribution is going to look like. So whether it's simple things like head position, mouth opening, there are some standards that are used from a mouth opening perspective, cough strength, if it's a single cough or multiple coughs, the droplet size distribution and number of droplets. There's a number of papers in the literature that talk to this type of analysis that look at droplet distributions that are single particle size. Those don't tend to give you the kind of results that you would hope, only because you're actually looking at, let's say, where one set of particles might go. And you really have to take into account a profile of particles, and I'll talk about that here in a second. So let's talk about what is the right approach. So we've been working with a number of agencies in Europe, in Asia, and here in the US to kind of come up with a methodology. So we've come up with a strategy which is a high fidelity Lagrangian approach with coupled multiphysics. The droplet modeling, we chose to use a standard distribution of both droplet sizes as well as velocities with a typical angle and mouth opening. And those, again, come from kind of a mean of the literature. From an airflow modeling, as I mentioned before, for looking at unsteady enclosed environments, one needs to have a converged simulation before you introduce the particles. Otherwise, it's difficult to get accurate propagation modeled. The cough jet has a time dependency, so the velocities are not static. The tracking over time needs to take into account evaporation, breathing, and the forces on the droplets. One thing to point out is that evaporation is critical, and we're not talking about evaporating water in this case. We're talking about saliva. So you have to take into account the multiphysics associated with, let's say, droplets of saliva versus droplets of water. And of course, then you want to look at a number of scenarios. So you can look at where people are in the cabin environment, the type of cough, whether or not barriers or masks are necessary. Initial results suggest, however, that the airflow is such in most modern aircraft that these particles do not persist for very long in this environment. So to accurately model a single cough is incredibly complex then. And oftentimes what you see in, let's say, the popular culture are simulations that may not be representative of what's actually happening. And they don't take into account either the exact geometries or the indoor or outdoor spaces that need to be modeled. So let's start with the cough jet profile. So we modeled the time-dependent cough velocities. This is multi-component. So we have air, water vapor, non-evaporative, so that's the contamination. We used a representative angle of, I believe, about 30 degrees with an average mouth area opening of about 4 square centimeters. On the right-hand side, you actually see the computational profile, and on the left-hand side, what you're looking at is the experimental data, which I think, and so we were confident that we are modeling the typical cough quite well from a velocity perspective. So let's take a look at some basic results. And okay, it's animating a little slower, but hopefully we'll let this go through twice just to make sure you get to see all of this. But basically what you're seeing on the right-hand side is a partial approach. This is a statistical strategy. It represents looking at what would be the equivalent of, say, 10 coughs. It's probabilistic rather than deterministic, so the total number of droplets tends to be somewhat high, even though the inputs to that simulation are in fact the same as the one on the left, which is looking at a discrete representation of those particles, where we're looking at 2,000 particles, which is typical for a cough. One thing to point out is that if you looked at the data on the right, you may be under the impression that there's this massive plume of particles that are released during a cough event. That's not an accurate representation. It's more accurate to look at the discrete particles as shown here. From an evaporation perspective, what you're seeing here is the table of droplet sizes we used. And this is from Moravska. She basically had determined not only the number of particles in each distribution bin in terms of the particle diameter, as well as the relative velocities or mass flow rates. What we have on the left-hand side is we're actually looking at those droplets over time and taking into account the evaporation. And you can see that the larger particles are actually evaporating and becoming smaller and smaller particles until they get into the 1 to 10 micron range, where they tend to persist. So the next question we had was, well, what about the use of masks? So this is actually some work that was done by Milovan Peric. He actually looked at the efficacy of a mask for respiration and cough, and the implication for mask design. And specifically, what Milovan was interested in was trying to understand what is the relative impact of masks that don't fit appropriately. So we use this as an input with his guidance to evaluate simulations related to masks in a cough scenario. So we chose to model this mask as a baffle interface. We included gaps on the side and top of the mask. We used a filtration efficiency assumed from a triple layer mask using viscous porous resistance. One of the things to point out is that most of these triple layer masks are actually very good at getting large particles, as you might imagine. However, when you get into the sub-micron or micron or below range, the efficiency of capture goes down quite a bit. You get into, say, the 50% range. If we just look at a side-by-side representation of the two cough events looking 1 second into the cough, you'll see that the impact of the mask on reducing droplet transmission is quite significant. You can see for the most part, the overall majority of those droplets are actually captured by the mask and do not leak into the cabin environment. So we use this as an input. And as I said, we have a couple of results that I haven't completed. So I'm going to just show you some preliminary results of this and open it up to questions. So basically, then we looked at those two cough events in a cabin environment. And one of the things that we did is we included those gaps with the loose fitting cloth mask based on the data that we'd already run with a single passenger, and then looked at where do those droplets go. So a couple things to point out. On the left, you can see that, in fact, most of the particles during the cough event are captured. Very few make it into the cabin environment. On the right-hand side, you see a unobstructed cough. The majority of those droplets, as in the first example I talked about, end up falling to the ground. But the cabin airflow typically comes from the top and goes down. So most, if not the majority, of those droplets actually get pushed out of the ventilation system. The exhaust for the aircraft is actually below the feet on the side. All right, so unfortunately, as I said, there were a couple of results that I was hoping would have finished, and we ran into some IT issues two weeks in a row, which really suck, but I guess it is the way of the simulation. But as I mentioned, we will be presenting those results with a partner in September. But just to summarize quickly, so we talked first about the idea of using a mixed fidelity approach to understand a way to model the ECS system design. So that includes, at the system level, understanding ECS pack efficiencies to help us improve overall cabin environment in terms of air circulation, filtration, cooling efficiency. Then we talked a little bit about the modeling the local cabin environments and the discussion of how to model human coughs. So we've actually developed a couple of models that we will share with those people who are interested, which actually go through that whole process I went through and have the complete simulation set up. So if you're interested in modeling coughs in any environment, for that matter, or even respiration, you can actually use these models to look at simulations. These are CFD models, so if you're not doing CFD, this may not be your cup of tea. And the last thing I'll leave you with is that cloth masks, triple layer cloth masks, are very effective in reducing airborne droplets and aerosols. And we have data now to suggest that in an environment where everyone's wearing a cloth mask, for example, on an aircraft, the probability of inhaling these droplets is extraordinarily small. We're talking hundreds, tenths of, or I'm saying 10,000ths of a percent, something to that effect. Very, very small. So I, for one, am confident that if when we are allowed to travel again, we all start traveling, we should be safe. And with that, thank you. I went over. Sorry. Thank you to the organizers, and I'll open it up to questions.
Any questions for Dr. Rittenberg?